Greetings, math fans. Alright, so this is next topic here in calculus, and it's called continuity. So if a function is continuous, okay? So we're going to talk about two different things. One is continuity at a point, the other is a continuous function. So starting out here, continuity is a point, and basically what we're going to be doing is we're going to be using calculus to show continuity. You have two different kinds of points. You have interior points and you have endpoints. And just to describe a little bit with a quick graph, okay, in other words, if I have a graph like this, these are endpoints of a graph, and then anything inside of that is an interior point, okay? So in order to prove that a point is continuous at that point, a couple things have to happen here. Actually, one thing, these two things have to be equal. Okay, and the first one is limit as x approaches c. Remember, this is a two-sided limit. All right, and a two-sided limit means you approach it from one side, from either side, and they have to be the same. So basically, the one-sided limits must be equal. Okay, so again, coming from the left side and coming from the right side, they have to go to the same location. That has to be true in order for a two-sided limit to exist. Okay, and then f of c is actually when you're there at that point. Remember that? So if I said f of 5, that means you say, hey, I'm actually at 5. What is the value of y? As opposed to the limit, meaning, hey, I'm approaching it from one side or the other. That's what a limit is, versus I'm actually there. Okay, so that's what an interior point is. That those two have to equal, the two-sided limit and f of c have to be equal. For an endpoint, you can't think about it. Let's look at the right endpoint here. Okay, I certainly can't say that a two-sided limit has to be equal to f of c, because what's happening when we're coming from this side? Well, remember, the two-sided limit here really doesn't exist because I'm not coming from the right side. I'm only coming from the left side. So that's why you can't use that. The equality here for an interior point is the same as an endpoint. Okay, so if I have a left endpoint, which is right over here, a left endpoint, basically I can only come from the positive side. So notice that little plus sign there, math fans? Limit as x approaches c from the positive side. So I'm coming from the positive side, and that has to equal f of that value. Okay, for an endpoint. Now, same thing if I'm coming from the right endpoint. So this guy right here, it's my right endpoint, and I have to come from the negative side, which means coming from the left. So that has to equal f of c as well, which is that point. Okay, so again, interior points, look at the two-sided limit, got to be equal to f of c. Endpoints, you're only coming from one side, and it's got to be equal to f of c. Okay. So let's take a look at some examples here of, I made a nice graph for you, and you can kind of see this graph here. It goes from -2 to 4. It's got all kinds of holes and jumps and all kinds of stuff here. So let's take a look and see, basically let's compare the limits and then determine if it's continuous or not. Okay, so let's kind of move this up a little bit. Alright, so the first one, it's a left endpoint, x equals -2. And what we're doing is we're looking at the limit as x approaches. Now, because it's an endpoint, I can only come from the positive side. So x approaches -2 from the positive side of f of x. Well, what is that? Well, I mean, if you look at it, you guys should be really familiar with limits now. Remember, I'm approaching -2, so what's the value of y? Well, the value of y is 0, isn't it? And what about f of -2? Remember, we're actually looking at f of that value. Well, see, you look for the solid dot. So f of -2 is equal to 0. Because these are equal, this is a continuous function, or continuous at that point. Okay? It's pretty easy. Now we're going to switch over to x equals -1. That's an interior point. So now we're going to start looking at two-sided limits. So limit as x approaches -1, and there's no plus or minus because it's a two-sided limit. First of all, does that exist? Well, do you guys agree as I approach -1 from the left side and the right side, the value is equal to 2? Okay, because they're both sides going towards 2. And what is f of negative 1? Well, look for the solid dot. Isn't that equal to 1? Okay, since these are not equal, we say it's discontinuous. I'm going to abbreviate that as DC. All right, it's just a lot easier to write that down. Okay, so it's either continuous or discontinuous, and here it's discontinuous. The next one, I'm just going to cursor down here a little bit, but it's x equals 0. So let's take a look at it. Do you guys agree that, again, I'm coming, so let's kind of highlight this, right? Here's 0, and I'm coming from the left side and the right side. It's equal to what? The limit? It's equal to 0. And what's f of that value? What's f of 0? Well, it's also 0. So we say, again, limit as x approaches 0 of f of x is equal to 0, and f of 0 is also equal to 0. Again, these are equal. Okay, these are all interior points now until we get to x equals 4, which is the right end point, and we can say that's continuous. Okay, pretty easy. Let's look at x equals 1. So x equals 1 is basically right here. And what can you tell me about the two-side limit? You should tell me the two-side limit doesn't exist, because coming from the right side and coming from the left side, right, they're different values. One is positive 2, one's negative 2. So right away you guys can tell me that the limit as x approaches 1 of f of x does not exist, because the one-side limits are different. And I don't even care what this is, though you can figure it out. F of 1, go back up to the graph here, f of 1 is wherever the solid dot is, which happens to be negative 2. Not that it really matters again, but of course, just because of D and E, this is discontinuous. Okay? So again, in this guy here, the one-sided limits are not equal. Okay, so let's keep going here. X equals 2. Again, another interior point, so now we are right here. And sure enough, I mean, look at it. The limit, let's write it out here. The limit as x approaches 2 of f of x, again, it's a two-sided limit. Well, they're both going to 0, aren't they? And what is f of 2? Well, it's also 0. So again, these are equal. It's continuous. Okay, x equals 3, right here. Okay, same thing. Left hand and right hand limits are equal. They're both going to negative 2, and f, so we can say that limit as x approaches 3 of f of x, okay, the two-sided limit, that's equal to negative 2, and f of 3 is also equal to negative 2. Looking for the solid dot. Again, these are equal. It's continuous. Okay, let's go to x equals 4. It's a right endpoint. So remember, it's a right endpoint, so we're only doing a one-sided limit. So we're right over here. Okay, and we're only doing a one-sided limit. We're coming from the left-hand side, and that has to be equal to f of that value. Well, isn't f of that value where the solid dot is? So they're not equal, right? We can write here that limit as x approaches 4, and again, it's from the negative side, right? Because the one-sided limit, that of f of x. And again, if you look at that, go back to it, right? It's equal to 0, right? Because look at the limit. Okay, it's equal to 0. And what is f of 4? Well, it's where the solid dot is, and that solid dot is at 2. So these are not equal, so it's discontinuous. Okay, and the last one is x equals 5. And you're like, what? X equals 5 is not even on the graph. You're right. X equals 5 is somewhere out here. In fact, it's not in the domain, and if it's not in the domain, it can't be continuous out there, because it's only defined in that between negative 2 and 4. So what you would actually write for this one, it's you tell me it's discontinuous, and you would say it's not in the domain. Okay, so that is what point discontinuity is all about. Really not very difficult. But just remember, you got to compare the limits and the f of some value based on whether or not it's an endpoint or an interior point. Okay? All right, so let's keep going. So now we're going to talk about continuous functions. Okay, so it says outputs vary continuously with inputs and do not jump from one value to another without taking on values in between. That's what a continuous function is. Now you got this big old graph here, and I even said use your stylus and draw a line. Don't lift your stylus. This is a continuous function. So in other words, I can draw this function, you know, like this, as long as I don't go vertically, right? Because it's got to be a function. This is a continuous function. As soon as I pull my pen off the paper and I create a gap or something like that, and it's a jump here, it's not continuous anymore. So continuous function is you never take your pencil or your stylus off the paper. Okay, we got some different types of discontinuity, and again, discontinuity means where the function is not continuous. So the first type is we're going to make a graph here. And we're going to go down to, we're going to make this guy here. And so what happens is this is called a point discontinuity. And this happens to be right here, a point discontinuity at x equals 2. Now it's a point because I mean, it basically is one point. Here is the point. You have to basically lift up your pencil off the paper just for a split second, and then you jump over and you keep going with your function. But it's basically a hole. In fact, it's an important thing to write down here. Point discontinuities are holes. Okay? The next type of discontinuity is called an infinite discontinuity. And we'll do the exact same grid here. And here's an horizontal asymptote, and here's a vertical asymptote. And if I draw my graph, it looks like this and like this. So you would say there's an infinite discontinuity basically at x equals 2 again. And basically an infinite discontinuity is a vertical asymptote. Okay, because you can't cross that asymptote, right? Your pencil jumps from one spot, this guy right here. It can't really cross that asymptote. It keeps going down, but then it continues on the other side of the asymptote up on top here. So it can't cross it, and you call that an infinite discontinuity. Okay, and then the last type of discontinuity is a jump discontinuity. And we're going to do the same grid here. And you guys probably should recognize this nice little friendly graph. Looks like that. And like that. Okay? That's a jump discontinuity. And basically, you guys should kind of recognize is this type of graph, absolute value of x over x, or in this case here, it's absolute value of x minus 2 over x minus 2. But it's these kind of functions, and it's also piecewise functions. And I'll put on here sometimes. That's a jump discontinuity. Because sometimes a piecewise function connects, right? If I give you another example, here's a piecewise function, and then it connects like this, right? In the spot here, that wouldn't be a discontinuity. But as soon as it doesn't connect, something like this, and then like this, now it's a jump discontinuity. Okay, so you would say in this case your jump discontinuity at x equals 2. Okay? So those are 3 types of discontinuities. And again, I try to explain what each one was, right? A point discontinuity is a hole, an infinite discontinuity is a vertical asymptote, and a jump discontinuity is where it just jumps from one value to another. Okay, there's no asymptote, it just jumps from one value to another. And then we have something called a removable discontinuity versus a non-removable discontinuity. And basically a removable discontinuity is you can make the function continuous by filling in the hole. Only point discontinuities are removable. So go up to the spot here. Number 1 is a point discontinuity. It is removable. The reason it's removable is because I can basically make this function continuous. Well, how do you do that? Well, we can get rid of this point here, and I can take it and I can plug a hole here. I can plug a hole. It is now continuous. That's why it's a removable discontinuity, because they can remove the discontinuity and make it continuous. Okay? The other type of discontinuity is non-removable discontinuity on the right here. You can't make the function continuous. So basically this is an example is an infinite and a jump discontinuities are non-removable. So look at these. There's no way you can connect these two together because one's going down and one's going up. It's basically crossing an asymptote, and you can't jump through the asymptote, okay? Because it would be undefined. So that's why it's non-removable. I cannot, with a single stroke of my stylus, I cannot plug that hole because there's not really a hole, but I can't plug it and make it continuous. Same thing with the jump discontinuity. There's no way for me to connect these two. Now some people say, Mr. Curvis, well, why don't you connect it with a vertical line? Boo! If I connect it with a vertical line, what happens? It is not a function anymore, okay? And it's got to be a function. So that would be again a non-removable discontinuity. There's no way I can take my pen and plug that hole, and again that makes it a non-removable discontinuity. So again, number one, point discontinuity, I can plug the hole. Removable discontinuity. Number 2 and 3 are non-removable because they cannot plug the hole. Okay, very, very important. So on a quiz and test, basically I'll say, hey, what type of discontinuity is it? Is it a point, infinite, or jump? I won't even tell you the names. You just have to tell me. And then I'll say, okay, now once you told me that, tell me, is it removable or non-removable? And then you got to make the determination. If it's a point, you can remove it. If it's an infinite or jump, it's non-removable. Okay. All right. On the bottom here it says, note when showing discontinuity graphs are required. You can't just tell me it's discontinuous by observation. Okay, you can't just do that. The AP graders won't like that, and I won't like that either. So you have to actually make a sketch to show me discontinuity. So let's do some problems. It says make a sketch of each function. Then for number 1 is for what values of x is f of x discontinuous. Identify the types of discontinuity, which means a point, an infinite, or jump. Then state whether these discontinuities are removable or non-removable. Okay, pretty easy. So this first function, if I graph this, okay, it's going to look like this. And basically, you're going to say, well, the only place it's discontinuous is basically where it's negative. So you're going to say it's discontinuous at, and then you're going to use interval notation, negative infinity to 0. Okay, not including 0, because at 0, it's continuous. Because you can look at the limit coming from the positive side, and you can say f of that value, and they're going to be the same. They're going to be below 0. But once you go to the left of that dot, there is no more function for the square root of x. So you're going to say, again, discontinuous in those two values, and you're going to say not in the domain, just like the one problem I did before, not in the domain, and is a non-removable discontinuity. Okay? The next one, y equals cube root of x. Well, I don't know if you guys remember how to graph that. But the cube root, it's not undefined in any place because it's the cube root. You could take the cube root of a negative number or a positive number or 0, and but it does look something like this. Okay, where when x gets really big, y gets big a lot slower. Okay, because the cube root of 8 is 2. Cube root of 27, 3. So x got huge, but y only jumped up 1. Okay, so where is this not continuous? Well, it's actually a continuous function. Okay, because there's no issues at all with the function. It's continuous everywhere. Never lifted up my stylus. It's perfect. Okay, let's look at the next example. It's a nice little piecewise function. So I'm going to graph it, and we need some points here. So if I plug in a 2, I get 2, 1. And I put a 2 in there, I get negative 2 plus 4 is 2. So 2, 1 and 2, 2. And let's graph these guys. So the 2, 1 is going to be a solid dot. And it's greater than 2, so it's up 1 over 1. All right, so that's that graph. Okay, and then I'm going to plot 2, 2, and then of course that's going to be an open dot. And then the slope is negative, so it's down 1 to the right 1 or up 1 to the left 1. And that's my graph. Okay? So that's the piecewise function. So what type of discontinuity is it? Well, first of all, you're going to tell me it's discontinuous at x equals 2, which is kind of really where piecewise functions are discontinuous, where it changes its value. And you're going to tell me it's a jump discontinuity, because it is jumping from one value to another, and it is non-removable discontinuity. Okay? So 3 things really are telling me where it's at, that it's a jump discontinuity, and that it's non-removable. Okay. You guys should be super familiar with this graph. Ugh, so familiar. If you're not sure, man, you get plot a few points, and you know negative 1's the bad number, but I can pick a number -2 and 0. Okay, so -2 gives me -1. Absolute value is 1. 1 over -1. This is -1. This is undefined, and 0 gives me absolute value of 0 plus 1 is 0, or is 1 over 1 is 1. Okay, so now if I graph this thing, it's going to be at -1, right? That's where it switches. So it's, think about this, right? This at -2, when you go more to the left, the arrow goes to the left, and otherwise it goes to the right. Right, and I can plot those points. If I want -2, -1 is right here, and 0, 1 is right here. So that's my graph. And of course, what type of discontinuity is it? It's a jump discontinuity as well. So we're going to say discontinuous at x equals -1. It's a jump discontinuity, and it is non-removable discontinuity. Okay? Not bad. And last one here is a nice little rational function. Again, you guys should be really good at drawing all these different kinds of graphs. So the first thing I'm going to do is I'm going to factor this baby. Okay, so you're going to get x plus 5, x minus 3, over x plus 3, x minus 3. So you can see I can cancel it out. Once you cancel it out, math fans, make sure you recognize that you have a hole, which is going to be a discontinuity. So you're really graphing y is equal to x plus 5 over x plus 3. Okay? And, you know, we're going to get our vertical asymptote is going to be x equals -3. And the horizontal asymptote is going to be, because it's x over x, it's going to be y equals 1. Okay? So if I graph this, y equals 1 is going to be here. And x equals -3 is going to be here. And then remember, you make a t-chart, because I want to know what's going on either side of that vertical asymptote. I'm going to pick -4, I'm going to pick -2. So I pick -4, I get -4 plus 5 is 1. 1 over -1 is -1. Put -2 in there, -2 plus 5 is 3, and then -2 plus 3 is 1, so it's basically 3 over 1, which is 3. Okay, so I plot those points. So -4, -1, and -2, 3. So -2, 3. So your graph, and don't forget you have a hole here. You have a hole at x equals 3. So let me just label that in here. So at 3 someplace, I'm going to have a hole. So this is what my graph looks like. And like this. Okay? So now we can talk about discontinuities. So you gotta show me a graph. You can't just say it's discontinuous because of blah blah blah. You gotta show me some proof, either analytically or graphically. So you're gonna tell me it's first of all, there are 2 points of discontinuity. Okay? Make sure you identify all points. Because here's the deal, math fans. I'm not going to give you 2 blanks when there's 2 discontinuities. Okay, there's just going to be 1 blank there, and you're going to have to draw another blank. I'm not going to just give it away. So you make sure you tell me both of them. So you're going to say discontinuous at x equals -3, and it's an infinite discontinuity, and is non-removable. And then you can just say there's discontinuity at, and this is going to be our hole at x equals 3. So x equals positive 3. And that is a point discontinuity. And is removable discontinuity. Okay, because I can remove that hole, I can plug it, and now it becomes a continuous function. Okay, so this is a good one because it's got two different types of discontinuities. Okay, so that's it for different types of graphs and everything for discontinuities. And I have one more problem here, math fans. This last problem says find a value of a that makes the following function continuous. Well, remember, if it's continuous, then especially with the piecewise function, it matches up. So basically, these coordinates need to be, the y coordinate has to be the same. Okay, so what I'm going to do is, because this is y equals, I'm going to set those two equal each other. So I have basically x squared minus 5x plus 2. That y value's got to equal 3ax plus 4. That's the other y value. Okay, they have to be equal. So what I'm going to do is I'm going to substitute x equals 2 for that, and basically what I'm going to do is I'm going to solve for a. So we got 2 squared minus 5 times 2 plus 2 equals 3 times 2 is 6a plus 4. Okay, and then let's simplify it. So we get 4 minus 10 plus 2 equals 6a plus 4. So 4 minus 10 is negative 6 plus 2 is negative 4. So subtract 4, you get 6a is equal to negative 8. And so basically a is equal to negative 6 over 8, or negative 4/3. And that's your answer. What value of a makes the following function continuous? It's negative 4/3. Okay? So it's really not that bad of a lesson. Kind of just know a little bit about continuity, what makes it continuous, and be able to graph functions and talk about three different types of discontinuity, which is a point discontinuity, an infinite discontinuity, and a jump discontinuity, and then tell me, is it removable or non-removable? You also talk about interior and exterior points with continuity at a point. And then the last problem was find a value of a that makes the following function continuous. Okay, and that was really easy. Okay, so that's it about continuity, math fans. Hopefully that's you're good to go here, and have an outstanding day. Adios. Goodbye.